Welcome to week number 8 for ECE 111, Introduction to ECE. In this lecture, we look at problems you run into in Circuits 1, EE206, and how to solve those problems using Matlab. Just reiterating, ECE 111 is one of the courses offered at North Dakota State in the Department of Electrical Computer Engineering. To get to that, go to Bison Academy, that's the semi-official website for the Electrical Computer Engineering Department. Click on 111, and that takes you to this course. So what we've been looking at so far is problems you encounter in Algebra 1, Trig, Linear Algebra, Calc 1, Calc 2, finally circuits. When you get to Circuits 1, it's kind of a big deal. For example, these are the courses that you take as a computer engineer. You start out in the math sequence, go through the math sequence, and eventually you wind up right here. This is kind of the gateway course. As soon as you get through Circuits 1, you start taking courses in electrical computer engineering. Now, that's kind of the reason you went into engineering. You want to build stuff. Once you get through Circuits 1, you're going to start building stuff. That's where it gets fun. So this is where you have something to look forward to. When you get to Circuits 1, you'll be looking at problems like this. This is an electric circuit. I've got a voltage source, resistors, and I have unknown voltages, unknown currents. One of the problems you try to solve in the first part of Circuits 1 is how do you find these unknown voltages? How do you find these unknown currents? And the trick is like the old story of the fire extinguisher and trash can. If I can set up the problem as n equations and unknowns, I can solve. So we'll be beating that technique to death. To find the unknown voltages, I try to write 4 equations for 4 unknowns, then I can solve for the 4 unknown voltages. For the currents, I have 4 unknown currents. If I can write 4 equations for 4 unknowns, I can solve the currents. That's kind of one of the things you do in Circuits 1. Today we're going to look at voltage sources, current sources, and resistors, how to combine the resistors in series and parallel, how to use conservation of current, conservation of voltage to find voltages. In addition, we'll be looking at a program called Circuit Lab that lets you simulate circuits like this. So before we start out, let's do a couple definitions. An atom is made up of protons and electrons. Protons are in the nucleus, along with neutrons. They determine the atomic mass, the atomic number, and the properties of the material. The electrons are in shells around the atom. The electrons form covalent bonds, and when an electron escapes its covalent bond, it's free to move throughout the crystal, carrying current. Current is the flow of electrons. The electrons are negative charged. That's because Faraday took a guess as to what the charge was, got it wrong, and we've suffered ever since. So when electrons flow left, current flows right. 1 amp is 1.6 times 10 to the 19th electrons per second. A huge number, so from our standpoint, basically current looks like it's continuous. It's actually discrete, but when you deal with numbers this large, it looks like basically infinity. Voltage is the force that causes current to flow. So 1 amp flowing across 1 volt produces 1 joule. It determines the energy released as current flows. And resistance limits current flow. So the basic equation is V equals IR. 1 volt is 1 amp flowing across 1 ohm. An analogy that's often used is water. If I have 2 tanks of water, water flows from the high tank to the low tank. The difference in height is the head pressure. That's analogous to voltage. The flow of water is analogous to current, and the resistance to water flow, the thickness of the pipe, is resistance. Now in terms of voltage sources, there's 3 different symbols that are used. A circle with a plus and minus. This kind of symbolizes the plates that Faraday was using. He would use zinc, tin, zinc, tin, zinc, copper, something like that. As you have the plates, they would form a galvanic cell, producing voltage. This kind of symbolizes the plates that Faraday was using. Or a circle with a squiggle through it, that's an AC source. So for a voltage source, there's a couple different voltages. To give an idea what voltage means, 1.5 volts is the voltage across the AA battery. That's enough to turn on a single LED. 5 volts is the USB battery. That's enough voltage for a computer. 13.2 volts is a car battery. That's enough to turn on a motor, a car starter. 120 volts is a wall outlet. That's enough to power a computer, a hairdryer. 13,200 volts is a residential transmission line. That's enough to power a small subdivision, enough voltage to kill a person. And 345,000 volts is what's used for long-distance transmission lines, enough to power a small city, create an arc about 11 centimeters across, really fry a person. That's a voltage source. Current sources. Current is the flow of electrons. Current determines the brightness of an LED, determines the torque on a motor. So if you have an electric car and you hit the gas pedal, you're specifying the current of the motor. More current, more torque. 1 microamp, well, the diameter of a wire determines how much current it can carry. 1 microamp is a wire that is 0.7 microns across, really, really tiny. That's the sleep mode in a TV remote. 1 milliamp is a wire 21 microns across, power a single LED that's fairly dim. 1 amp is a 0.7 millimeter wire. That's how much you use when you charge your cell phone. 1 amp, or 10 amps, is a 2 millimeter diameter wire. That's a hairdryer. And 10 or 100 amps is 7 millimeter diameter wire. That's used for welding. In terms of power, power is measured in watts, or energy is watts. 1 milliwatt is the power on indicator LED on like your TV remote. 1 watt is the human heart. 100 watts is a 1,000 lumen LED light bulb. 100 watts is typically how much you output when you bicycle. A Tour de France athlete will output 300 watts. 1 kilowatt is for short times a person can output 1 kilowatt. Or the amount of energy a hairdryer uses. 10 kilowatts is a lawn tractor. Now, resistors. At the start of circuits 1, we look at resistor circuits. How do you analyze a circuit made up of resistors, voltage sources, current sources? The basic equation for a resistor is V equals IR. The voltage across the resistor is the current times resistance. The power that it dissipates is volts times amps. It's also I squared times R. Now, all materials have innate resistance. For example, take a piece of copper. Copper has a resistivity of 1.7 times 10 to the minus 8 ohm meters. Meaning, if I take a piece of copper wire that's 100 meters long, 1 millimeter diameter, the resistance will be the resistivity times 100 meters, gives you meters squared, divided by the area, the meter squares cancel, gives you ohms. That 100 meter long piece of wire is 6.8 ohms. The way resistors are built is use a thinner wire and wrap it around a core. That's kind of what this symbolizes. And I get 6.8 ohms in a smaller package. The way resistors are marked is through color codes. Each color corresponds to a different number. And if you have 3 numbers, what that means is the first 2 numbers is the mantissa, the second one number is the exponent. So this would be 10 times 10 to the 2 ohms. This is 1 kilo ohm. If there's another band, that's the tolerance. So for example, suppose I had these resistors. What's the value of that resistor? Well, to do that, use the color code. This is brown, black, yellow. So this is 10 times 10 to the 4th ohms, or 100K. Next one. Green is 5, blue is 6, orange is 3, so this is 56 times 10 to the 3, or 56K. Next one. It's 2, 2, 1. That's 22 times 10 to the 1 ohms, 220 ohms. And last one. White is 9, brown is 1, red is 2. So this is 9.1 times 10 to the 2 ohms, 9.1K. That's kind of how color codes indicate What they're useful for is you can look at a circuit and see what the resistance is just by looking at it. Or in the lab, if there's a big pile of resistors, you can scrounge through it and find the ones that you want. Another thing we'll be covering when you get to Circuits 1 is Circuit Lab. This is something that we're going to start using from now on in this course. Circuit Lab is a really friendly drag and drop program. Circuit Lab is free for all NDSU students. When you register, just use your NDSU email address and it'll be free for you. When you launch Circuit Lab, you get something like this. It's a drag and drop program. If I want to build a circuit, I can just kind of drag and drop the elements over. If I hit R, that rotates the element. Let's do kind of a simple circuit like this. I need a ground reference. Again, all voltages are relative to ground. Ground's important. Without a ground reference, voltage doesn't really mean anything. Once you get the circuit components in there, I can just connect up the wires. When there's a connection, you see that little dot. That means these wires are connected. To change the value, just double click. Let's call this one V0 and make that 10 volts. R1, let's make that 200 ohms. Let's make this one 300 ohms. 4K, 4,000 ohms, and 5K. Once you have your circuit, I can then add labels if you want. I kind of prefer this because it then makes the problem looks like the homework problem. So let's call this node V0, V1, V2. That's how you build your circuit in Circuit Lab. Really easy, just drag and drop. Once the circuit's in Circuit Lab, I can then analyze it. If I go under Simulate, under DC, this is the steady state DC analysis. I can look at different things. Like here, when I look at voltage V0, V1, V2, analyze. It says V0 is 10 volts, 9.19 volts, 8.67 volts. What we'll be looking at later on next week is how do I calculate that? Can I calculate the voltages and see if they match Circuit Lab? Another thing I can look at is the current. If I get rid of these and double click and click on the left side of the resistor, that'll ask me what the current is, going left to right. Run DC Solver. This current is 4.03 milliamps. This is 1.73 milliamps. That's Circuit Lab. When you take Circuits 1, Circuit Lab can be used to check your answers, see if you did it right. We'll be using it in this class to check your answers as well. So we'll analyze your circuit on paper, analyze using Matlab, then check to see if I did it right. Your answer should match up with what Circuit Lab tells you. So again, Circuit Lab, that's your drag and drop. We did that. Connect the components, find the values. To analyze the circuit by hand, to see if they match what Circuit Lab did, there's really 4 different techniques. There's conservation of voltage, conservation of current, simplification of resistor circuits, and voltage division. For conservation, well, to start out with the definition, a voltage node is all the voltages, or all the voltages that are shorted together. The resistor ideally has no resistance, so the voltage at this point should be the same as anywhere on that blue wire. The voltage on this point is anywhere, will be the same anywhere on the red wire, or a purple wire, or a black wire. So there are actually 4 different voltage nodes. One of them is ground. Ground is important. Ground defines what everything is relative to. Now, ground has 2 symbols. If you see a circuit with 2 different symbols, that's kind of warning you that there are 2 different ground references. They're not necessarily the same, such as the circuit ground might be different than earth ground. Ground, again, is important. If you think about birds on a high voltage line, they treat the 13,000 volts as ground. We treat the earth as ground. They're different. Sort the 2 grounds together, the birds go poof. So you need to know what the ground reference is. In Circuit Lab, if you don't have a ground reference, it'll complain to you. You need that ground reference. Now, in terms of techniques to analyze a circuit, the first one I'm going to look at is conservation of voltage. What that says, if I take a voltmeter, take the 2 leads, short them together, I get 0 volts. If I go around a circuit and wind up back where I started, all the voltages added together have to add to 0. That's conservation of voltage, or Kirchhoff's voltage law. The trick to analyze the circuit is find a loop where there's one unknown. Around this loop, I know minus 100 plus V2 plus V3 equals 0. That's one equation, two unknowns. Doesn't really help. Around loop A, I've got one unknown. So I know that minus V3 plus 35 plus 44 equals 0. That lets you solve for V3. And that's the trick in this circuit. Try to find any closed path where there's just one unknown. So like this would be, well, that's two unknowns. This is another path with one unknown. Let's kind of look at it, see if you can find a path with one unknown. To do that, I would start with loop A. Around loop A, I have minus V3 plus 35 plus 44 equals 0. If I hit the minus sign first, I subtract. Plus sign first, I add. That lets me solve for V3. V3 is 79 volts. Around loop B, minus 44 minus V5 plus 16 plus 22 plus 15 equals 0. That lets me solve for V5. V5 is 9 volts. Around loop C, now that I know V5, I can solve for V4. Minus 8 plus V4 plus 9 minus 35 equals 0. I know that V4 is 34 volts, and so on. That's conservation of voltage. So here's a handout. Try to find the unknown voltages A, B, C, D, E, F. Let's pause it right here, let you try to solve, then we'll continue. Okay, so first find one unknown, a loop with one unknown. And here's one. So know that minus 22 plus 31 plus A minus 17 equals 0. Solve for A. Tells me that A is 8 volts. Or this way, 39 volts is 39 volts. Around this loop, I now have one known, B. Minus A, or minus 8 plus 24 plus B minus 26 equals 0. Solve for B. Gives you B is 10 volts. I can now go around this loop. Minus 10 plus 7 plus C minus 31 equals 0. Solve for C. This is 34 volts. Around this loop, two unknowns. Let's not do that loop. Around this loop, one unknown. Minus 100 plus 17 plus D equals 0. This is 83 volts. Minus 83 plus 26 plus E equals 0. So this is 57 volts. And finally, minus 57 plus 31 plus F equals 0. This is 26 volts. It's kind of like a Sudoku puzzle. Try to find paths where the voltages add up. Once you're done, any path works. So if I pick anything weird, like this path right here, I'm back where I started. All these added up should be 0. That's conservation of voltage. The second rule is conservation of current. Conservation of current says current in equals current out. Current is the flow of electrons. If electrons aren't being created or destroyed, if I have 100 amps flowing in, and it flows out 3 different ways, all these 3 together must add up to 100. Current in equals current out. That's conservation of current. So if I have this circuit, for example, I can solve by saying current in equals current out. So zooming in, get over to it. There it is. I know 100 amps is going in. This has to be 100 amps. Let's see. Find another place where there's one unknown. Here's one unknown. 100 in. I've got 100 going out. So I2 plus 20 plus 35 plus 40 must be 100. So 75, 95. This must be 5. 100 in gives you 100 out. At this point, I've got 25 in, I've got 25 out. 5 goes this way, this must be 20. At this point, I've got 20 plus 35, 55 in. I have to have 55 out. I4 is 55. And finally, at this point, 100 goes out. I've got to have 100 going in. 5 plus 55 plus 40, 100 in, 100 out. That balances. That's conservation of current. So try that with this problem. Try to find the unknown currents, I1, I2, I3, I4. So doing that, 100 amps in, 100 milliamps in, I have to have 100 milliamps going out. 100 in, I have to have 100 out. 20 goes down, 80 goes right. 80 in, I have 80 out. So I3 plus 15 is 80. This is 65 milliamps. 65 in, I've got to have 65 out. This is 35. 35 in, I have to have 35 out. Conservation of current. For resistor circuits, the basic equation is V equals IR, and from that I can do I is V over R is V over I, and one way that's drawn is like this. V is I times R, V over I equals R, V over R equals I. Given 2, I can find the third, and the fourth equation, power, is volts times amps. So we have 2 of these numbers, I can find the rest. For example, 10 volts at 2 ohms, take the ratio, 10 volts at 2 amps, take the ratio, I get the current. The current, resistance is 5 ohms. Power is volts times amps, 20 watts. If I know these two, let's see. That's a little bit trickier. I can also say power is I squared R. If I substitute V is I times R, I have I times R times I squared R. I know 5 is 20 times I squared. Grab my calculator. So 20, correction, 5 watts divided by 20 ohms. That's I squared. Take the square root, it's 0.5. So this is 0.5 amps. Voltage is I times R. This is 10 volts. If I know volts and ohms, I know current. Volts divided by ohms is current. 10 over 5 is 2 amps. 10 times 2 is 20 watts. If I know watts and amps, I know voltage. 6 watts, 2 amps. That must be 3 volts. 3 volts over 2 amps is 1.5 ohms. So given any two, I can find the other terms. Now when I have a resistor circuit, I can simplify it. If I have resistors in series, they add. And one way to see that is conservation of voltage. Vn is V1 plus V2 plus V3. Assuming this current, again the current through R1 has to go through R2, has to go through R3, conservation of current. That says I times R1 plus I times R2 plus I times R3 is V. Pull out the I. V is I times the sum of the resistances. This is the net resistance. So resistors in series add. Resistors in parallel. These are a little bit trickier. They add as the sum of the inverses. And you can see that IA is I1 plus I2 plus I3. I1 is Vn over R1. I2 is Vn over R2. I3 is Vn over R3. Factor out the Vn. Solve for V equals IR. Voltage is I times the sum of the inverses inverted. So that's the net resistance. The sum of the inverses inverted. So resistors in series add. In parallel, the inverses add. Take the inverse. With that, I can simplify a circuit like this. Here I have to find out which ones are in series, which ones are in parallel. In series, the current through this resistor goes through that one, These are in series. In series, they add. This is 600 ohms. These are in parallel. In parallel, the inverses add 1 over 300 plus 1 over 600. Take the inverse, 200 ohms. So all this together gives you 200. This is in series. Anything through 100 goes through all this mess. In series, they add. The total is 300 ohms. Now, in Matlab, I could solve just as well. In Matlab, I would take 400 plus 200, that's 600, in parallel with 300. So let's call that RA is 1 over 300 plus 1 over 600, 200 ohms. In series with 100 is RA plus 100, 300 ohms. This is also where the HP calculator really comes in handy. So the HP calculators that kind of push, they really help when you get to tests. This is RPN notation. There's a couple calculators. There's the DM42 on Amazon, the HP Prime, the Pre42. This is the one I like. It's free. It's on your cell phone. Shortly, we'll have one of these you can buy from the department, just a kit you can build for like $10. With RPN notation, to add these, in series they add. Actually, kind of backing up. The way the calculators work, there is no equals button. This uses a stack. When I hit plus, minus, times, equals, it affects x and y. So when I add 2 plus 3, I first have to set up the stack. I do 2, enter. That pushes that on the stack, then 3. 2 and 3 are on the stack. I can now add them. If we have the number 4, that takes the number 5, pushes it on the stack, and 4. 5 and 4, when I multiply, I get 20. If I want to divide by 7, I hit the number 7. 20 divided by 7 is 2.8. That's kind of how HPs work. For this circuit, I want to add these together. I would do 200, enter, 400. That's on the stack. In series, they add. In parallel, the inverses add. So take the inverse, take 300, inverse. The inverses add, take the inverse. This is 200 ohms. In series with 100, 300 ohms. That's an HP 42 calculator, simplifying this. I can check my answer in CircuitLab. Build the circuit, apply test voltage. Once you have the test voltage, see how much current draws. The current draw is 3.33 milliamps. From V equals IR, I know the voltage, I know the current, I can find the net resistance. 1 volt divided by 3.33 milliamps is 300 ohms. Same thing we calculated right here, 300 ohms. That's how you find it in CircuitLab. This is actually how an ohmmeter works. An ohmmeter applies a test voltage, sees the current draw, and calculates the resistance. So let's solve this one using Matlab. In Matlab, let's take 200 in parallel with 300. Call that RA is 1 over 200 plus 1 over 300. That's 120 ohms right here. In series with 500, that's 620 ohms. In parallel with 400, RC is 1 over RB plus 1 over 400, 243 plus 100. .343 ohms. That's solving in Matlab. Second example. Here's a resistor circuit. Find the resistance between A and B. The trick is to find the resistors that are in series and parallel. Let's bring that back over here. So here, these two are in parallel. So let's take 200, inverse, 300, inverse, add the inverses and invert. So all this together is 120 ohms. In series with 500, adds, gives you 620 ohms. So all this together is 620. That's in parallel with 400. In parallel, the inverses add. Take the inverse, 400, inverse, add, All this together is 243 ohms. In series with 100, 343 ohms. So the total resistance is 343. This is kind of why I push the HP calculators. They get the right answer and they're quick. So it's going to do that from scratch. If this is a test, this is kind of what you're going to see when you take circuits 1. Find the total resistance A to B. I would look at this and say 200 in parallel with 300 in series with 500, add. In parallel with 400, take the inverse, 400, inverse, add, inverse. In series with 100, done. Try doing that with a Casio or an HP calculator, or a TI calculator. It ain't nearly as fast. In Circuit Lab, I can check my answer. Apply 1 volt, see what the current draw is. The current draw is 2.914 milliamps. From B equals I times R, voltage divided by current, gives you 343 ohms. Same answer I got on the calculator. So here's the challenge. Find the resistance between A and B. So let's find the total resistance in Matlab. That's 200 in series with is 200 plus 300, 500. In parallel with 400, in parallel you take the sum of the inverses. It's 1 over RA plus 1 over 400, 222 ohms. In series with 100, 322 ohms. In parallel with 500 is 1 over RC plus 1 over 500. Total is 195 ohms. Let's pause for a sec and let's just solve that problem. Okay, let's find the answer. Starting out, I've got 200 in series with 300. So 200, enter, 300, that's 500 ohms. In parallel with 400, take the inverse, 400, inverse, add inverse. All this together is 222 ohms. In series with 100, adds, this is 322 ohms. In parallel with 500, so take the inverse, 500, inverse, add inverse. All this together is 195 ohms. And that's my answer. So the total resistance is 195.94. And again, let's show you, if this is a test, what that would look like. Start your stopwatch. I would say, starting out, 200 and 300 in series. I can actually add that in my mind. I don't have to use a calculator. 500. In parallel with 400, inverse, add inverse. In series with 100. In parallel, inverse, 500, inverse, 195 ohms. Done. Next problem. That's kind of why I say HP calculators are worth 10 points on a test. It's really quick on problems like this. More importantly, it works with complex numbers, something we're going to be covering in a few weeks. Other calculators really struggle. Okay, so that's combining resistors in series and parallel. The next two topics would be how to analyze the circuit to find the voltage. There's two tricks. One is called voltage division. If I want to know what is the voltage of V3, is the voltage, is the resistance that I'm measuring, divided by the total resistance, that percentage of Vn. Where that comes from is if I have Vn, the current is Vn divided by the total resistance. The voltage is I times R. Or rewriting it is what I'm measuring, R3, divided by the total resistance times Vn. If you forget that equation, think about the extremes. If this is 0 ohms, I should get 0 volts. If this is 0 ohms, that works, so that's consistent. Where that's useful. Suppose I want to find what are the voltages V0, V1, V2, and V3. I can use voltage division to do that. If I knew V2, I could find V3. It's what I'm measuring, 200 over 230 times B2. But I don't know B2. If I knew B1, I could find B2, find all this resistance, then use voltage division to find B1. Don't know B1, so let's use all these together, find that resistance, voltage division to find B0. That I can do. Once I know B1, then find B2. Once I know B2, then find B3. So here's the procedure. First, so let's try to solve using Matlab. I know that the resistance from 3 to ground is 200. Between 2 and ground, that's resistance looking right. That'd be R2 is 1 over 150 plus 1 over 230. That's 90 ohms looking right. At V1 looking right, it's R1 is 1 over 100 plus 1 over 20 plus R2. 52 ohms. Now I can use voltage division. So that's 10 volts, 10 ohms. I know that V1 is what I'm measuring, R1 over the total, R1 plus 10. 10 ohms right there. That percentage of 10 volts. In this parentheses, 8.4 volts. V2 is R2 divided by R2 plus 20, that percentage of V1. V3 is 200 over 200 plus 30, that percentage of V2. That's finding the voltage using Matlab. Let's find the resistances. So let's grab my calculator. The resistance at this point looking right is just 200 ohms. At this point looking right, the resistance is 150 in parallel with 230. This is 90.78 ohms. And let's do store O2. That's the resistance at B2. At this point looking right is that resistance plus 20 and parallel with 100. So take the inverse, 100 inverse plus 74.4 ohms. Let's do store O1. Okay, now I can use voltage division. It's V1 is equal to what I'm measuring, 74 ohms, over 10 plus 74, that percentage of B0. So let's do recall O1, enter, 10 plus, there's 10 plus B1 divided by B1. Kind of show what I just did there. I did recall O1, that's the first voltage, enter, that creates 2 copies on the stack. Now add 10. This is the other entry on the stack that was up there. Take 74 over the total, that percentage of 10. So that is 8.81 volts. Now let's do recall O2. That resistance, enter, 20 plus, that's the denominator, there's the numerator, take the ratio, that percentage of 8.81, 7.22 volts. B3 is then 200, enter, 30 plus, divide, that percentage of 7.22, 6.28 volts. So by using voltage division, I can find the voltages. And also kind of notice, this is a pretty slick calculator. It worked really well for that. Try doing that with the TI. There's the answers. In Circuit Lab, I can build a circuit and check my answers. They should match. So here's a practice problem. Find the voltages V1, V2, and V3. Again, to do that, Let's find the resistances. So this is 200 ohms, looking right. This one looking right is 230, in parallel with 200, 106 ohms. Let's call that store O2 for B2. At node B1 looking right is that plus 30 in parallel with 200 is 81 ohms. Store O1. So to find the voltages, use voltage division. 81 ohms over 81 plus 30. Enter 30 plus slash that percentage of 10 volts, 7.30. At B2, do recall O2, 106, enter 30 plus slash that percentage to 7.3, 5.7 volts. At B3, 200, enter 30 plus slash that percentage of 5.7, 4.96 volts. Voila. HPs are pretty impressive. So that's basically week number 8. For resistor circuits, the stuff we're going to be covering at the start of circuits 1, the basic equations are V equals IR, power is volts times amps. Resistor circuits can be simplified. In series, they add. In parallel, the circuits add as the sum of the inverses inverted. You can do that in Matlab, but really this is more of a calculator type problem. At any node, current in equals current out, that's conservation of current. Around any closed path, the sum of the voltages must add to 0. Plus, using voltage division, given the volts at one point, I can find the voltage elsewhere. Again, this is something you could do in Matlab, but really when you have one equation and one unknown, a calculator is a lot easier to use. And in my book, the HP42, best calculator ever made for electrical engineers, this makes solving these problems really easy. That's the type of problems you can expect on tests. So when you get to circuits 1, make sure you have a calculator that can solve these problems. I recommend the HPs. This is the HP42. There's another calculator called the HP Prime. This one is still in production. It is $130 on Amazon. Not quite as nice, but still pretty nice. To use this as an RPN calculator, you go Shift, Settings, and then under Entry, I want to be RPN. That's reverse Polish notation. I can then do these similar things. If I have, let's go back to that problem. Yeah, where are you? Nope. Go back to this problem. I can say these resistors together are, oops, settings, home, there we go. Let's take 230. Here's the inverse button. Inverse. What's going on here? 230. There it is. I was out of RPN mode. That again. 230. Inverse. 200. Try again. 200. Inverse. Add. Inverse. That's 106 ohms. Add 30 to it. Take the inverse. 200. Inverse plus inverse 81 ohms. So to get the first one, I'll take 81 over 81 plus 30. Here's 81 plus 30. Take the ratio times 10. First one's 7.3 volts. Now take the next one, the 106. enter, enter, plus 30, plus slash. That percentage is 7.3, 5.7 volts. And then take 200. Enter, enter, 30, plus slash. That percentage of 5.7, 4.9 volts. Another version of RPN. But that is lecture number 8 for ECE 111. Some of the problems you run into in Circuits 1.